Alright, today is July 31st, 2018, and what we're going to show here is basic working parameters for an FCOG1200 board at low power. What we're going to do first is we're going to power the board with 24 volts AC on positions 1 and 2 of J6. When we first power, the board will have the 3 LEDs on. Got power, the board is inhibited, and then we will have a phase loss. There it is. Thank you, Karen. Now at this point, this is just with 24 volts AC. We're going to bring in our own phase reference via J7, and we temporarily have our board inhibited. So you can go ahead and enable it now, Tony, using your test box. So let's go ahead and take a look at the signals on J7. What we do is we simulate the 6 signals. In this particular case, with this box, we have square, looking at channel 1, square waveform. There we have a 50% duty cycle at 60 Hertz on J7 position 1. Then we want to go to J7 position 2. Here's another one, 120 degrees apart. And then the third one, 120 degrees apart, and then we go to a J7 position 4, 5, and 6 for the other 3 phase references for the Y secondary of that transformer. So with those phases, we can see square wave, 50% duty cycle, 120 degrees for the first 3, and then 30 degrees phase shifted from the first 3. With that information, we're going to walk the circuit. We just show what J7. Again, these signals can be square waveforms, or they can be sinusoidal waves, about 2 to 5 peak-to-peak voltages coming here. Now, the next stop we're going to go is we're going to go to U5, position 2, and we're going to take a look at the effect of the filter, the RC filter, on those reference that we brought in at J71. So this is the RC filter. Then we're going to go across to U5 pin 15, which turns out to be test point 5. And what we have to have, this is how we're going to check that U5 is working. We have to have a 50% duty cycle, especially the big difference is when you bring in for reference a sinusoidal waveform, and then at the output of U5 you have a square waveform that is 50% duty cycle. And one thing that we can do is we can check at U5 positions 15, 14, 13, 12, 11, and 10 to check all 6 phases, and all of them have to be square waveforms, 50% duty cycle, 120 degrees from the first set for the first 3 sets, and then 30 degrees apart for the second set. So that's if U5 is working okay. The next thing on the circuit, we're going to take a look at the phase loss detection circuit. And this is the way it works. We basically have a window comparator, we have 2 thresholds, and then the 2 phase loss signals will have to be within the thresholds. This is something that we've done before. So first we're going to go to U6 pin 7, and that will be the upper threshold. We can see that it's already marked with the first marker. Then that's the 7 volts, and we're going to go to U6 position 4. That's the lower threshold. That's approximately 5 volts. Now that's basically checking. Now going to test point 15. Test point 15 is the phase loss signal for the X bridge, and we notice that that signal has to be inside that window. I mean, we could open up this and zoom it in, but we would decide to show it just the way it is. Now we're going to go to TP16. TP16 is the same. It's the signal that will be the resulting reference signal from the Y bridge, that it's also going to be compared against the threshold. So there it is. If under these conditions, under these working operation conditions, the resultant signal is not within this threshold, that's when you have a phase loss. Tony, you want to go ahead and throw in a phase loss now? See, just the fact that got distorted, that's just enough to be outside that threshold. And then we have here on our board a red LED, and this is basically the condition that you have. You have a red LED, the board will never enable. You notice that. Go ahead and clear the enable, and we looked at it, the LEDs. If we cleared the phase loss, the board was already commanded to enable. The board will enable. But if we bring in and induce a phase loss, the board will immediately inhibit. Okay, go ahead, Tony. Now, we can also take a look at the ultimate output of the phase loss detection circuit, either at CR3 or at J6 position 5. In this particular case, we're going to be looking at R43. And we see that under normal conditions, that would be a solid signal at 12 volts. And when we induce the phase loss, depending on how bad the distortion is, these lows will be the places where that phase reference signal, either from the X or from the Y, it's outside the window comparator. Notice that when we right now we have a phase loss, we don't have an output. When we clear the phase loss condition, we have an output. By the way, this channel 4, it's basically looking at J1 between positions 3 and 4, and what we do is we have a 4 ohm resistor right here. So we're basically loading that output, and we're looking between 3 and 4, that firing signal. We have 2 train pulses that are 30 degree in length, 30 electrical degrees, separated by 30 degrees. We are at 5 milliseconds per. So if we were to do this, we'll see the pulse string. I could come here and shoot the other one. Now let's go ahead and take a look at test point 2. This is another way to verify that the board is working okay. Test point 2 has to be a sawtooth waveform that has the same number of peaks and valleys as the number of pulses on the board, in this particular 12 from here to here per cycle. And as a function of sync high, the command, go ahead Tony, it's going to be convoluting on itself. It's going to be rotating. It's going to be changing by itself, but always around 5 volts. This is a voltage controlled oscillator. Now the last thing that we're going to point out is test point 5. It's the plus AX reference out of U5 position 15, and the resulting delay angle command will be on test point 7. And let's pay particular attention to this. This is the 50% duty cycle. This is the reference that we bring in through J7, whether it's a sinusoidal waveform or whether it's a square waveform. But already at test point 5, it's always a square waveform. Here we have the delay angle command. We notice that the firing of the delay angle, go ahead Tony, as we start increasing, we change this delay and we start advancing or firing. Go ahead and bring it back to 0, Tony. You're at 0. So here we have.
I'm full on right now.
You're full on. Okay. Bring Sikai to me, okay. So here what we have is our delay angle is maximum. We notice that we start here. This is where we are starting to fire. Go ahead and start increasing, Tony. We are reducing the delay. We're basically getting it as close to this. So this, we're advancing the fire, and that's why the SCR is conducting as part of the sinusoidal waveform. So this, hopefully these signals will help you troubleshoot your board. This is the end of this video.